What specific problem does the bot architecture aim to solve in the context of robot policies? And how is this problem related to existing learning architectures that have been used in robotics?
The bot architecture aims to solve the problem of inefficient utilization of spatial interrelations between sensors and actuators in robot policies, which is often overlooked by existing learning architectures that primarily adapt methods from natural language processing or computer vision. Traditional robot policies, including those based on vanilla transformers, do not leverage the robot's embodiment structure, leading to suboptimal performance in tasks requiring corrective localized actuation. In contrast, BOT incorporates a masked attention mechanism that allows each node, representing sensors and actuators, to attend only to itself and its direct neighbors, effectively modeling the robot body as a graph. This design enhances the inductive bias for policy learning, resulting in improved steady-state performance, generalization, and computational efficiency compared to standard architectures. By addressing the limitations of previous approaches, BOT demonstrates superior performance in both imitation and reinforcement learning settings, particularly in real-world applications.
How does the body transformer, BOT, work? Illustrate the methodology step by step, detailing how the masking mechanism is implemented and how it interacts with the sensory inputs and the transformer architecture.
The body transformer, BOT, operates by modeling the robot body as a graph, where nodes represent sensors and actuators, and edges reflect the body morphology. The methodology begins with a tokenizer that projects sensory inputs into corresponding node embeddings, assigning global quantities to the root and local quantities to limb nodes. The core of BOT is its transformer encoder, which utilizes a masked attention mechanism. Specifically, each layer is equipped with a binary mask that allows a node to attend only to itself and its direct neighbors, constructed as M equals I_n plus A, where I_n is the identity matrix and A is the adjacency matrix. This masking introduces sparsity in the attention computation, enabling efficient information flow from local to global contexts across layers. Finally, a detokenizer converts the output features back into actions or values, ensuring that each node's output is tailored to its corresponding actuator, thereby enhancing the overall performance and generalization of the robot's learning policies.
Can you provide a simple example that demonstrates the inner workings of the BOT architecture, illustrating the process of mapping sensory inputs to actions through the tokenizer and detokenizer?
The body transformer, BOT architecture processes sensory inputs through a structured pipeline involving a tokenizer and a detokenizer. For instance, when a robot receives sensory data, the tokenizer maps this observation vector into a graph representation where each node corresponds to a specific sensor or actuator on the robot's body. This mapping assigns global quantities to the root node and local quantities to the limb nodes, followed by a linear projection that generates node-specific embeddings. After the transformer encoder processes these embeddings, the detokenizer takes the output features and projects them back into actions associated with each limb's actuator using separate learnable linear layers. This structured approach ensures that the actions generated are closely aligned with the robot's physical embodiment, allowing for effective control and response to environmental stimuli.
What are the theoretical or practical benefits of using the BOT method compared to traditional transformer-based architectures or MLPs for policy learning in robotics?
The body transformer, BOT method offers several theoretical and practical benefits over traditional transformer-based architectures and MLPs for policy learning in robotics. Firstly, BOT incorporates a masked attention mechanism that leverages the spatial structure of the robot body, allowing each node to attend only to itself and its direct neighbors, which enhances the inductive bias and leads to improved steady-state performance and generalization. Secondly, BOT demonstrates superior scaling properties, as evidenced by its consistent performance improvement with an increasing number of trainable parameters, indicating a reduced tendency to overfit compared to vanilla transformers. Additionally, BOT outperforms MLPs and traditional transformers in both imitation learning and reinforcement learning tasks, showcasing its efficacy in real-world applications, such as deploying policies on a unitary A1 robot. Finally, the computational advantages of BOT are significant, with near 200% reductions in runtime and floating point operations, flops, due to the sparsity of the masked attention mechanism, which optimizes the training time of learning algorithms.
How is the performance of the BOT method validated in experiments? Please specify the datasets, benchmarks, and metrics used to evaluate its effectiveness in both imitation learning and reinforcement learning settings.
The performance of the body transformer (BOT) method is validated through experiments in both imitation learning and reinforcement learning settings. In imitation learning, the BOT architecture is evaluated using the MoCaPac dataset, which contains over 5 million transitions of action-labeled humanoid state trajectories. The effectiveness is measured by mean returns normalized by the length of a clip and the normalized length of an episode, with results showing that BOT consistently outperforms MLP and vanilla transformer baselines, particularly on unseen validation clips. In reinforcement learning, BOT is tested using the Proximal Policy Optimization (PPO) algorithm across 4 robotic control tasks in Isaac Gym: humanoid mod, humanoid board, humanoid hill, and A1 walk. The average episode return during training is used as the primary metric, with BOT mix demonstrating superior sample efficiency and performance compared to MLP and vanilla transformer baselines across these tasks.
What were the most significant results achieved with the BOT method, particularly in relation to performance improvements over baseline models, and what implications do these results have for future work in robot learning?
The most significant results achieved with the body transformer (BOT) method include its consistent outperformance of baseline models, such as MLP and vanilla transformers, in both imitation learning and reinforcement learning settings. Specifically, in the imitation learning experiments on the MoCaPac dataset, BOT demonstrated superior generalization capabilities, with performance gaps widening on unseen validation clips, indicating its embodiment-aware inductive bias effectively enhances learning. In reinforcement learning tasks, BOT mix showed improved sample efficiency and asymptotic performance across various robotic control tasks, while BOT hard excelled in simpler environments, suggesting that the architecture can adaptively leverage body structure for different task complexities. These results imply that future work in robot learning could benefit from further exploration of embodiment-aware architectures, potentially leading to more efficient and robust learning policies that are better suited for real-world applications. Additionally, the computational advantages of BOT, such as reduced runtime and floating point operations, highlight the potential for scaling these methods in practical robotic systems.